Well, hi everybody, and welcome to this VEX V5 webinar. In this webinar, we are going to discuss some advanced programming techniques using VEX C++ and the VEX EDR V5. So if you are a competition team or if you help coach a competition team, these are things that might be helpful to you. Specifically, we are going to talk about two topics. One is a custom user interface, so using the touch screen on the robot brain to be able to take input and do something meaningful with that. And then the second is operator assist. So even whenever you're driving the robot, you can use sensor feedback to help improve that. So those are the two main topics for today. So first, custom user interfaces. The V5 robot brain screen is incredibly nice. It serves as both an input and an output. Whenever we say that it's an input, it is able to detect touch, just like a touch screen, like on a smartphone. And whenever we say output, it is able to output text, shapes, pixels, that you have a whole lot of control over. So it is great for user interfaces, and you can customize your own with a little bit of programming. The screen itself is 4.25 inches diagonal. It's full color, and it has 480 by 272 for the resolution. So that's basically the number of pixels or the image size that we're able to work with whenever we create a custom user interface. The only thing to be aware of is the top 32 pixels are used up by the status bar at the very top of the screen. So where it says graphics on my screen and 222, uh, those are taken up. So we can't count on those top pixels as part of our user interface design. It has to be below that. Now, before I jump right in and talk about the code and the user interface, which is pretty long, I wanted to cover some of the basics with displaying text to the screen and then displaying shapes to the screen. So, if you already know that, hold on with me. We'll get to the fancier stuff here in just a little bit. Okay, so outputting text to the screen is very simple. We can use the brain.screen.print command to output text. Our program starts at the top with int main. We're able to print the message that we want. We make sure to specify that in between the double quotes, and then our program ends. One thing to know about the screen is even when your program ends, the screen does not automatically clear. So if you have experience with previous robot platforms, the VEX Cortex or the any other systems out there, you might expect that at the end of the program, the screen would clear, and so we would never observe this text. But actually, with the V5 and VEX C++, this message to us will continue to stay on the screen. So um, part of user interfaces is often displaying text. Maybe you want to make it fully graphical. We'll get to that next. Okay, so VEX C++ also has the ability to display shapes to the screen. You can output lines, you can output rectangles, you can output circles, you can even do individual pixels. What I have on this slide here is showing using the screen to output specifically a rectangle. The first thing that we define on line 5 is the fill color for a shape, so what it will be on the inside. Line 6 is the outline color or the pen color, so any shape that we will draw will have a red inside and a blue outline. And then finally on line 7, I display the thing that I want to display. In this case, it's a rectangle. We know that based on the command draw a rectangle. That will be drawn at position 1010, and it will be 100 pixels wide by 100 pixels high. So if you wanted to draw a button on your robot brain, you might choose to use a rectangle in order to do so. All right. And then the last kind of subcomponent that I want to draw attention to is detecting the touch. So the previous two pieces of code were outputting text and then outputting shapes that we could use to draw things on the screen. Those were both using the screen as an output. We also want to use the screen as an input. So uh, there's a very simple command, brain.screen.pressing, that is just true if you are pressing the screen or false if it's not. This program that I have right here is actually one of the sample programs built into Vex Coding Studio. Check it out, it's really cool. Whenever you press the screen, it will draw a circle on that spot. So it shows you how responsive the screen can be. Now notice that we're checking if it's pressing, but also if you look on line 16, we can see exactly where the screen is being pressed. We can get the X position of the press and the Y position. And so that's how it is able to draw a circle at the origin of the press. All right, so those are the fundamentals of outputting on the screen and getting input. Uh, I want to show some sample code that we have written that combines these to create a custom user interface. Okay, so this is kind of a long program, much more than I could fit on a single slide. So I did break it up over several slides. Now, you might be asking, how is this strategically advantageous to a competition? How does this help me? Well, inside of the VEX Robotics competition, you may want to have many different autonomous routines. The VEX V5 allows you to store 8 different user programs on the robot brain. So you could store 8 different programs on the robot brain with different autonomous routines built in. The downside of that is you have to keep 8 programs all in sync as far as the user control goes. So even if you have totally different, um, even if you have totally different autonomous routines, whenever the competition switches over to driver control, you have to put that code inside of every single program if you do this through separate programs. And if you make a change to one, you have to go back and update, all 8 of those if you have 8 separate programs. By combining the different autonomous routines that you might have, if you're on the red alliance or blue alliance, if you're on the right starting spot versus the left starting spot, depending on if your partner robot is able to shoot targets or if they're able to push or whatever the case may be, however many permeations of autonomous code you have, you can support that inside of your user program, inside of your one program, by building your own user interface. So that's kind of the justification and the advantage, is you can put it all in one code. There's not multiple things to keep up to date, to keep in sync with each other. You can maintain just one version of your driver control code if that's easiest. Okay, so all that to say, this program does that. What this program does is it draws 4 different buttons on the robot brain. And the code for doing that is on here. You can see that we're using variables to define some values. That way we can reuse those values multiple times. It also makes our code a little bit more readable. But then we are drawing those 4 rectangles in different sectors of our code. We have 2 that are red and 2 that are blue to represent 2 routines for the red starting points, 2 routines for the blue starting points. You could change this, expand this to be able to meet the needs of your team. Part 2 creates an infinite loop that checks where the screen is being pressed. Okay, so it waits for the screen to be pressed. Once it is pressed, it checks which quadrant that was in. Okay, so if it was in the top half of the screen or the bottom half of the screen, and then if it was in the right side of the screen versus the left side of the screen. And by figuring that out, by asking those questions using these if else conditional blocks here, we're able to tell which button the user selected. This next part is just a little bit of a confirmation screen on the robot brain. Uh, it says the program that was selected was 1, 2, 3, or 4, and then press again to actually run the code. Okay, so this just is kind of like a confirmation of the choice that the user made. And then finally, last but not least, we have something here called a switch case. A switch case allows you to run different sections of code based on a variable having different values. So here, we had stored the value of which button was pressed in the quadrant variable. So depending on whether you pressed button 1, 2, 3, or 4, you were able to choose different sections of code to run. So if you are writing autonomous code, if you have 4 different ones, you can just plop each of those under the respective cases. All right. Um, Now, to give you an idea of what this actually looks like, so you don't just have to use your imagination, I do have a picture here of what the user interface looks like. We have those 4 rectangles, 2 red, 2 blue. You can press in any one of them to make the selection. It confirms your selection and then goes ahead and runs the corresponding piece of code. So I think that sample code will be hugely beneficial to you if you are writing multiple autonomous routines. If you're not writing multiple autonomous routines, that's another great way that you can have a strategic advantage at these competitions to be more adaptive and versatile to the different circumstances you may encounter. Um, I will include a copy of this code alongside of the video so that you don't have to try to recreate it based on my slides. So look in the comments section, or rather the description section, for a link to the code, and then that way it'll give you a good start. The one thing to keep in mind, though, is if you do plan on using this code for a competition, you will still need to use the competition template. So the sample program that I showed here is not integrated with the competition template. That is something that you will need to integrate. All right. The second strategic advanced idea I wanted to give you was the one of operator assist. So, what exactly is operator assist? Oftentimes, I think sensors can be relegated to a role where they are only considered for autonomous if they are considered at all. But sensors can also be hugely valuable inside of remote control programs. You can do things like you can have it whenever you press one of the buttons on the wireless controller, trigger a series of actions to happen. You can have it drive forward until it's near a game object, align itself to that game object, grab it, and pick it up. And it can accomplish all those things with just a little bit of automation. So the idea here is that you are taking advantage of the things that the robot is good at, which is automation, getting sensor data, and helping that to give you a strategic advantage with your driver control, as opposed to putting all of the effort on the human drivers. The other big thing is whenever you're driving the robot, you may not have perfect visibility. Maybe another robot is blocking you, or maybe one of the field elements is blocking you. The sensors can really help with that. Okay, so for the little bit of code that I'll show you inside of this presentation, assume that we have a ARM motor set up and also a limit switch and a potentiometer. And again, we are combining these values with wireless controller values. So we have one of those in our program as well. All right. And then inside of this snippet of code here, I have a while loop, which is just repeating forever while true. And if you look closely at the series of if statements, you can see that I am checking first if I'm pressing a button. So the human, the driver, gets to still have the control over the intent. They control when the robot does the thing. But then inside of the condition for each of these if statements, I have added a second condition. In the top half of my program, with that first if statement, the condition is also checking if the potentiometer value hasn't reached a certain number of degrees. So basically, you can have it where the robot will lift its arm, but it will only go so high. So if you want it to have a stop that is before a mechanical stop, if you want to have it have a stop where the angle doesn't increase and you don't drop the object, if you, for any reason that you want to be able to control how high a mechanism goes, one sensor that you could use is the potentiometer. And it's very simple, relatively, to integrate this kind of code with that so that you can have a sensor make sure that you don't go past that desirable limit. A little bit below that, inside of the second if, we're doing very similar, but we are using a limit switch. Okay, so uh, the if the bottom button is being pressed, then the arm will only go down only if the limit switch is also not pressed in. Okay, so as soon as the limit switch gets pressed in, then it stops providing power to the motor. And then that's a good thing because then you're not trying to drive the motor up against the frame of your robot or another component. It keeps you from wasting energy and putting unnecessary stress on the motors. It also lets you know whenever you've reached the mechanical limit, whenever you've reached maybe the bottom of the rotation for the robot's arm. But again, the applications are as variable as the different robot builds are for VEX robotics competition. There's all kinds of different robot builds. There's all different kinds of styles of driving and styles of play. And so different sensors can be placed throughout the robot, and they can take some of that pressure off of the driver. They can assist the driver or, operator assist as they try to score points during driver control. So a few ideas for where you could take this, and again, there are lots. There's automatic pickup. So point your robot generally at a game object, push a button, and have it go forward and acquire that game object for you. You can make it even more reliable than a human driver with a lot of refinement. There's another one that I'm calling maintain equilibrium. So oftentimes, if you think about a 4-bar linkage or a scissor lift, it's important that multiple components of your robot move at the same rate, especially if they're being driven by multiple motors. So you can use sensors like the encoders to ensure that components within your robot are moving at the same rate, that the robot doesn't tip over, that it doesn't drop game objects that it's holding. And then another big one, I think, is just preset positions or angles. So for instance, in this year's game where you have to be able to shoot targets at different heights, it's pretty powerful if you can push a button on your wireless controller and have the arm or have the shooter on your robot go to a preset position. And then, based on the distance from the target, based on uh, the target that you're aiming at, you can have it go to one of these positions and have it properly aimed, and you can get a lot more reliable scoring out of your robot by having it go to those kind of preset values. So all of these are just instances of operator assist, where you can have sensors give you a strategic advantage inside of the competition. All right. So those were the big ideas that we were hoping to cover as part of this webinar. Thanks as always for joining in. If you have any questions, feel free to shoot those our way. And if you have any requests for future webinar topics, please feel free to shoot those our way too. Hope you all have a great week and good luck with your competitions.